and live streaming to the ether worlds of Facebook and the Wilderness Workshops Facebook page. So if there's anyone out there, we welcome them as well. So my name is Sarah Johnson, and I represent the Wilderness Workshop as an independent contractor, and I coordinate the Naturalist Nights for three different kind of overarching the three organizations that are put this all together. So those organizations are the Wilderness Workshop, the Aspen Center for Environmental Studies, and the Roaring Fork Audubon Society, which many of you are all members of either one or all three of those organizations, which is great. So as you know, Naturalist Nights is a 10-week speaker series. We're about halfway through, and we have a schedule. If you're interested in a schedule, find the ACES brochure that has a skier on the front of it. That's the best piece of paper back there with the full schedule, so make sure you grab one if you don't already have one. Each week, these happen on Wednesdays here at 6 o'clock in Carbondale at the 3rd Street Center, and they also happen up at Hallam Lake at ACES, or the Aspen Center for Environmental Studies, on Thursdays at 6 p.m. And so we're just so grateful our speakers are able to come and be part of, to do their talk twice. And each week this year, I'd like to add a land acknowledgement to our evening. So I would like to respectfully acknowledge this place where we are today in the Roaring Fork watershed, near the confluence of the Roaring Fork and the Crystal Rivers. It is here that the Ute people stewarded this landscape throughout the generations, and I think it's important that we remember that. So the Naturalist Nights, as I said, is a free thing, as you all know. It's more than tea and cookies. It's actually an evening of learning, and it all happens because of sponsors, such as tonight's featured sponsor, which is Aria's Loft, who has generously offered to house our speaker this week for free, which is wonderful, as well as all the other sponsors who make this possible. And that slide has been scrolling, so you'll see it in a moment. But many times the sponsors are in this room, and so I just want to make sure we make a thank you to our sponsors and appreciate them. So thanks to Aria's Loft and everybody else. And all those CMC students, please come in the door. You're all welcome. And everybody, yay! So there's a bunch of chairs. I'd like for all of you guys to grab a cup of tea and a cookie, and then please fill in all these chairs, especially up here in the front, because you'll be much more comfortable. But make sure you get tea and cookies first. So GrassRoots TV films this thing and each week, and then we're able to share. We have a whole library of Naturalist Night presentations from years past, as well as this year on our website. If you look for the videos on the Wilderness Workshop or ACES websites, then you can watch them, share them, watch years ago presentations, and just take advantage of that. It's quite a resource of knowledge as well as entertainment. You can fast forward through all the introductions because they're all about the same, and it's just me talking. Thanks for signing in at the door, and as you might remember, we offer continuing education credit for teachers or anybody who might need a continuing education certificate, and there's a special extra long sign-in sheet back there, so make sure your name and information goes on there. So before I introduce tonight's speaker, I would like to tell you about next week's. Next week we're going to talk about pikas, which are one of my favorite animals. And so Dr. Johanna Varner from Colorado Mesa University in Grand Junction is going to come and speak, and her title of her talk is Too Hot to Trot, Pika Ecology in a Time of Global Change. And maybe you have been part of the Pika Citizen Science Project. I have been, along with some other folks from around the community, and I hope that if you are, that you'll definitely come next week so we can learn more about pikas. But without further ado, tonight, since you all came for tonight's speaker, we have Liz Schnackenberg, who is from Steamboat Springs. She is the South Zone hydrologist for the Medicine Bow Routt National Forest, based in the Steamboat there in Routt County. She has over 25 years of experience working as a hydrologist for the U.S. Forest Service, and she has a bachelor's degree in geology from Colorado College and a master's degree in watershed science from Colorado State University. Her work focuses on the effects of land management activities on watershed, hydrology, and wetland riparian condition. She has been a member of the Colorado Riparian Training Team since 2004. She has worked internationally in Mongolia, China, and Georgia on wetland conservation and past flood planning. She's also worked on a place called Basalt Mountain, where there was a fire called the Lake Christine Fire. And in that place, and here locally, she served on a BAER team, and a BAER team stands for Burned Area Emergency Response. But before she worked on the BAER team here, in 2009, she was sent to Australia to work on a BAER team to help with post-fire effects planning. The Australians now have their own BAER program. In December 2017, she traveled to Portugal to help with post-fire planning following unprecedented fires, and returned in February, just a year ago, as a Fullbright Specialist to provide additional assistance. I wonder if she's going back to Australia anytime soon. So it's an honor to welcome Liz to our community and have her share with us so much of what she knows. So thank you so much, Liz.
All right, well, thank you, Sarah. Am I speaking loud enough? I know I can sometimes be quiet. Okay. Louder, better. Okay. Anyways, so I really appreciate the opportunity to be here. And I have to say, the Roaring Fork Valley has been a special place to me. I grew up in Denver, and my folks used to bring me up, and we'd go to Snowmass. In the summers, I stayed at Snowmass Falls Ranch, or I don't know, some ranch, and we'd go horseback riding, we'd go hiking, and cool. That's not the Perrys. It is. Marge and Bill, how are you? So that was my first introduction to the Roaring Fork. But then in college, one of my best friends from college is Katie Turnbull. And so fortunately, I got to spend some time with Katie here in the Crystal River Valley at that point. And so anyways, I love this area. So it's an honor to be here. And Sarah, is this slideshow? Okay. It's an honor to be here. And my day job, yes, I'm a hydrologist with the Forest Service, but actually tonight I get to just play because I'm just here for fun, if you will. And so I'm going to kind of play on a theme of catchments and watersheds. And where this kind of concept started, or kind of started thinking about this, was when I went to Australia in 2009. Because in Australia, they talk about catchments. And so after 30 days of talking about catchments and working on catchments, you start to think about it. You go, I kind of really like this. Catchment makes a whole lot more sense to me, to be honest with you, than watershed does. So I wanted to just play on that theme a little bit, and we'll get started. And just a little bit, this cartoon that's on the front of my slide here, that's the Flintstones when they took a vacation to the Grand Canyon. And so the reason I like this slide is that, that's just, these landscapes are evolving, so there's a lot of natural evolution that happens. So we'll move on. So, I said I want to talk about catchments and watersheds. So we'll start with what's the definition of a watershed. And if you look it up in Merriam-Webster, there's a divide and draining ultimately to a particular water course or body of water. And the USGS Science School talks about a watershed, an area of land where if the water falls, it drains off to a common outlet. So if water falls in this point, it's all going to drain down there. Water falls up here, it all drains out there to the common outlet. That's a watershed. So what's a catchment? Merriam-Webster says it's something that catches water. Okay. But the USGS says the word watershed, it's often used interchangeably with drainage basin or catchment. I agree with that. They are often used interchangeably. But the question I want to ask is, the words may be interchangeable, but are they really the same thing? And so just kind of start with a few examples to think about. So this is Steamboat Ski Area. This is about what it looks like right now. End of January, lots of snow, right? Looks like lots of fun. Let's go skiing. But really, what this is our largest water reservoir. Our snowpack is the largest water reservoir that we have. So snow falls, stored in the snowpack. Come spring, it starts to melt. But as it does that, a lot of that, it's infiltrating into the soil. It's recharging, it's refilling the soil profile. That water works its way down through the soil profile, very slowly. And then it shows up in our streams at the end of August and September. That's our base flows. Why are the streams running today? When you go out the Crystal River, it's running. It's not because it rained last night. Yeah, maybe there's a little snow melting, but it runs even when it's super cold. It's running because it's that water that's infiltrated, made its way down there. So in addition to being fun, our snowpack is our largest reservoir. But what happens if you change something about that? So in this case, this is dust on snow. Changes the albedo, snow melts, it melts faster and starts to run off faster. It doesn't have as much chance to infiltrate. It's running off earlier. So this, I would say, is actually an example of shed. This is where the water is shedding, or the water is shedding, or it's a watershed. So moving on, or kind of thinking about just where climate change, just to touch on this, climate change is actually a shed situation in the context that I'm using it. You have less snow, you have more rain, so it's not being stored in our natural reservoir, which means that it can't recharge our soils, that kind of thing. So then we rely on reservoir storage, and we have more evaporation, not that natural recharge. And so that quicker runoff, generally leads to lower base flows. So another example of a catchment, a catch scene. This is the Upper River just above the town of Steamboat, and the actual, the actual river channel, you can see it meandering through here. But what's happening over here, it's a large floodplain. So that big slug of water comes down, it spreads out on the floodplain, and several things happen. One is it loses its energy. So that erosive energy that comes with flooding, that just settles out on the floodplain. But the other thing that happens, really, is that that's recharging the groundwater. Again, so it's giving it time for the water to soak in, it's catching and storing the water. But if we look just downstream of that, so this is the area I just showed you at flood stage. If you look downstream where the river goes through the town of Steamboat, it's stuck between a railroad on one side and development on the other. It doesn't have its floodplain. So what is that water doing? It's not slowing down. It's not spreading on the floodplain. It's not infiltrating. All it's doing is shedding, or it's just moving through there as fast as possible. And then just to move on to one more example, catchment. So this is a healthy forest, right? And the Forest Service, the Organic Act, there were two reasons that the Forest Service was created. The first is the continuous supply of timber. The second is favorable conditions of flow. And those favorable conditions of flow are that ability to catch, store water, release it slowly, that kind of thing. So in here, we have an example of a catch situation. But this becomes a shed situation when a fire moves in. And so we lose that kind of healthy forest, some things change, and we're no longer storing water on the land we used to be. And so it's this is what I want to explore further in the rest of the talk. Just how the changes that happen between pre-fire and post-fire, and get more specifically in what causes that shed situation. So the effects of fire, going from a catchment to watershed, I think you probably know this, but wildfires result in that increased erosion, increased flood flow potential, increased debris flow potential, and an increased chance for weeds to move in. But why? Why does that happen? We know that happens, but why does that happen? And it's all because of changes in the soil properties. And so we'll talk a little more about those. Before I get into changes in the soil properties, though, just one thing that, and it's a terminology thing, but just to kind of hit on it, is that a lot of times people talk about a really intense fire. And they'll talk about 200-foot flame lengths, and it was a really intense fire. But that is not the same. That fire intensity is what's that energy or that heat release. But that's not the same as what we're looking at when we're talking about the effects on the soils and why things change. And so really what we talk about is fire severity. It's also what we refer to as soil burn severity, because it really is what are the effects on the soils. And so that is the effect of fire on the ground surface characteristics. So you can have a fire that runs through the grounds. It can be a running ground fire, 200-foot flame lengths. It could basically never touch the ground. And on the flip side, you can have a fire that just skunks along the ground forever, and it's not, not very big flame lengths, but that can actually have a big effect on the soils. So the intensity and the severity they're two different things. So this is an example. This is actually from the Lake Christine fire. When we flew the reconnaissance, you could see, looking down, it looked like, the crowns were burned pretty big. There's nothing left up there. And when you look on the ground, there's been a substantial change in the ground surface there, in the soil surface. So this is an example where the intensity and the soil burn severity were the same, in this particular area. But if we look at this one here, this is a photo from a fire in central Washington. And there was an inversion when this fire was happening. And so what happened is the inversion just kept the fire on the ground. And you can see the canopy is still largely intact. You can see the needles, you can see it's still there, but the ground surface, that's changed. So this is an example where we had a low intensity fire, it probably had 1 foot flame lengths, but it had a big effect on the soils, or in this case, a high soil burn severity. So soil burn severity, I've already said that it's the effect of fire on the ground surface characteristics, but the thing specifically that we're thinking about is how deep is that char? How much organic matter was lost? How did it change the soil structure? And how did that change infiltration, or the storage of water, or how much water moves into the soil profile? We use 3 categories, low, moderate, and high, and that's kind of get into those a little more. But the first thing, I'm up here talking about soil burn severity, and the reason why is that really determines, it's the soil burn severity, that change drives the rates of erosion, the flood risk, the geologic response, and recovery. But really the thing is, why do we care? Why do we care that these things change? And the reason why we care is, how does that affect those things that we care about? In this case, this is a culvert from the Himmen fire in 2002. Do we care? Is the culvert going to be overwhelmed? Did the flood flows increase enough? Yes, it did. This is a problem. We care. So how do we go about determining soil burn severity? The first thing we do is we start with satellite imagery, and it's called a burned area reflectance classification, a BARC map. And essentially what that is the satellite takes a pre-fire image and compares it to a post-fire image, and it looks to see how the reflectance has changed between those two. Because a green forest or pre-burn is going to look a lot different from a burned area. And the folks that work on this have actually gotten really good at calibrating these, and so they usually are a pretty good estimate of what's going on. So we'll start with the BARC map, and this is from the Lake Christine fire. This is the initial BARC before I even showed up. I had this thing in hand, and I was looking going, uh-oh. There's a fair amount of red and yellow on this, and it looks like we got some problems. But that's the satellite's opinion of what happened. What actually happened, well, there's only one way to figure that out, and that's to go on the ground and look. So the satellite gives us a good idea, gives us a good, where to start, and the pattern is usually really good, but we go to the ground to figure out, maybe we need a little calibration here. So the things that we're looking at when we're calibrating on the ground and thinking about soil burn severity, the field indicators, we'll look at the ash depth and the color of the ash. We'll look at ground cover, and that's not always so straightforward. We look at the roots in the soil structure, and we look at hydrophobicity. So hydrophobic, water repellency, hydrophobicity. So soil burn severity, the field indicators, and just some over comparison pictures here. Over here you can see we have low burn severity. The ground cover is intact, the roots, the soil structure is intact, it's holding together. We have good soil cover. Moderate, of course, is going to be that thing in between here. And then on the other end of the spectrum, though, you can see the ash, there is no ground cover. You can see that there's both a red and a gray ash there, and that the roots are consumed. This used to be a tree root that was completely consumed in this fire. So getting into those a little more specifically, so ash and ground cover. It's interesting, I didn't used to think about ash color, but it actually is a good indicator. When you start seeing red ash, then things burn really hot or really affected the ground. If you just see kind of black ash, that generally tends to be not as intense. That gray ash, that usually is pretty hot as well. The other thing, ground cover, so if you put something out in your garden, you often put mulch on it. Part of that is to protect it from raindrop impact, and part of that is to create that microclimate. So the ground cover, helps to protect the soil when it starts to rain, protects the soil from erosion, from that kind of soil sealing. So how much ground cover is left? And in this example, here you can see there's no ground cover to protect. Where over here, if rain hits, there's a lot of protection. The soil is going to be able to absorb some of that water. One of the things with fires, though, too, is oftentimes our ground cover is charred, but it's actually still intact. So while this may not look green and it's gray, that actually, if a raindrop hits that, it's still providing some protection. So those are the kinds of things we're looking at in terms of high, moderate, and low. So moving on to roots and soil structure. So soils have several things that hold them together. One is that there's a bunch of roots in them, and some of them are really fine, tiny roots, and then they get bigger and bigger, and then they're actual tree roots. But those roots, even those little guys, they're helping to hold the soil together. And the other thing that's holding the soil together is the organic matter content. So soils have, there's organics in it, and that actually creates this glue and creates what we call soil pedons. And so in this photo here, like these little clumps of soil that are holding together, that's the organic matter that's holding that together. And the other thing it does is by holding the soil together, it also creates those pore spaces that water can fill up, that infiltrates. So the organic matter and the role it plays in soil structure is huge. If we look at this picture, in this case, the soil structure, with the roots were totally consumed, so not holding the soil together, and the organic matter was melted, and it's no longer holding the soil together. So you can see these two, this shovel, these two places were right next to each other, and you can just see the difference in how now this is ready to erode and move on down slope. Over here in this picture, this is kind of in our moderate category. The soil structure started to break down and got hot enough, and so it starts to develop this kind of platiness. And when that happens, then the water just can't infiltrate as easily. So it starts to affect, again, that water infiltration when you get some kind of a precipitation event. So, and then lastly, the thing we're looking at, that hydrophobicity. And so hydrophobicity happens when that organic matter, I've already talked about, that kind of melts. And as that melts, that starts to drive down into the soil profile. As it drives down, it gets cooler as it goes down. And that's only no greater than 4 inches, usually 2 to 4 inches, or actually even less than that. But as it cools, when it moves down, it starts to kind of precipitate out, and it essentially shrink wraps the soil, if you will, and creates this plastic layer. It's like you put a layer of plastic down, and water can't infiltrate there. There are some soils that are naturally hydrophobic, but we definitely will see this hydrophobicity form after a fire. And you can see these water droplets here. That 40 seconds is kind of our cutoff. That's going to sit there, I don't know how long, but those, when those hit and they just beat up like that, that you've got those water repellent soils there. So those are the ground indicators that we're looking at. And so we use those ground indicators and we go, okay, here's what the satellite was thinking. We've been on the ground. Maybe we need to do some adjustments. And I really like the Lake Christine fire because it's a great example of kind of a variety in one fire. And what we saw was on the south end of the fire, on the south end of the fire, that it was in the pinyon juniper, graded up into the aspen, and then up higher into the conifers. But on that south end of the fire, the soils just really weren't as affected. Not to say there were no effects, because there certainly were. But the satellite was overestimating on the south end. So you can see that there was a fair amount of red here, and we just pulled it back some because the soils were still really relatively intact. However, on the north end, once you get up on the top of the Salt Mountain and draining down towards Cattle Creek, that was more of the conifers, and we saw things, that's where we had the huge ash, loss of soil structure, those kind of things. So on this end, we actually dialed things up. We said, no, satellite underestimated, or it's actually a little bit higher there. So that's how we take what does the satellite think and then boil that down. And, this gives us a pretty good idea of the effects of the fire in a very short time, because this is about a 2 to 3 day process going from satellite imagery down to a soil burn severity. So once we have our soil burn severity, what do we do with it? Well, we start thinking about how is that going to drive erosion. And so the erosion happens, again, you lose that ground cover, you don't have any soil protection or any ground protection, but you also, if you've lost that soil structure and the roots, they're not holding the soils together, so they're ready to move. And if the water isn't infiltrating because there isn't the pore space available because of those hydrophobic soils and because there isn't a ground cover that's acting as a sponge, there's more water that's running off over land. So all of that overland flow combined with soils that nothing's holding them together leads to a lot of increased erosion. And these are photos, both these photos are from Portugal, but you can see just where you have erosion starting at the top and just continuing down the hillside there. In low to moderate soil burn severity, not to say you're not going to see any erosion, you are, but you're not going to see as much. It's just going to be lower. So it's all about degrees is really what we're looking at. So soil burn severity and pattern. The other thing that really matters and that we want to think about is if you have something where the entire catchment here or watershed, is burned, that there is nothing between the top and the bottom to stop things there or to slow things down, right? That's just going to keep going. And in this case, there's a village. This is also in Portugal. There's a village sitting at the bottom. It's like, ew, that's not a good thing. On the flip side, this photo, this is from Oregon. You can see, yeah, there's going to maybe be some erosion, but this area, it's going to hit this unburned area. This erosion is going to settle out. It's not going to make it down. It's going to have less of an effect downstream on those things that we maybe care about. So it's not only how much soil, how much burned at high, moderate, low. It's also what's the pattern. Where is that distributed in space? One thing though that we usually see, and these photos are from Lake Christine fire at the end of July, early August, as the fire was still burning, is these systems did evolve with fire and they tend to recover quickly. So in those areas, especially of low and moderate soil burn severity, you often will see the green up happening. In the high, that's going to be tougher. We've lost a lot of those soil characteristics. That's where we're going to see the problem. So a lot of times we'll see things greening up relatively quickly. Of course, that's highly variable. So I wanted to move on now. So that was talking about the erosion piece of it. I wanted to move on now to talk about changes in hydrology and those increased flood flows. And so, I've talked about it, but that ground cover, that's that sponge. So we've lost our sponge, so water's not infiltrating as much. We've lost our pore space, so there's nowhere for water to infiltrate, actually. And we've developed those hydrophobic soils in some places. All of those things lead to increased flood flows. So when we're looking at flood flows, just touch a little bit on the modeling that we use. There's two different models. One is this Wildcat 5, which is it's a simple spreadsheet, but they're all based on rainfall runoff models and curve numbers, which I don't know if any of you are familiar with that. And then a more complicated one is Agua. It's much better at spatially distributing things, but it's really hard to run. It's complicated. But I wanted to use this graphic from Agua because on a normal just rain, summer thunderstorm, the rain falls, you have the sponge, you have the pore space available, you don't have hydrophobicity, water will just infiltrate. And it just goes into the soil profile and not much of it makes it to the stream channel. But when you change things, post-fire, then you have the rainfall hit, and like I keep saying, we're not getting as much infiltration, we're getting a lot more overland flow, and so instead of infiltrating, it's just running off and it's ending up in that open channel. That's where we're getting those increased flood flows. And the things that really drive how big of those increased flood flows are going to be, or the things that we're thinking about, are the basin characteristics, our elevation change. The steeper it is, the faster water goes. The flatter it is, the slower water goes. So that's one of the key points. We're thinking about the soil burn severity. In particular, we're thinking about what we call a curve number. So curve number kind of represents what's the potential for water to infiltrate. And if you think about if you have a football field and it rains, water infiltrates pretty well. So that's what pretty low curve number. If you think about pavement, water hits pavement, it doesn't infiltrate, it's running off right away. That's going to be a pretty high curve number. And it's really those curve number, that's the thing that we change in the model between pre and post fire. And then the other thing that really drives how big of an effect is the precipitation. Both the amount matters, but really it's the intensity. How fast is that water hitting? If it's coming down slowly, it doesn't overwhelm the system as much. If it comes down in a hurry, it has a lot bigger effect. So on the storm distribution, this is an example of, if you think about you have an inch of rain in 1 hour, well, is that 1 inch that's just consistently falling over the whole hour, which would be the straight line? Or is that 1 inch where we get a bunch of it to start with and then less on the back end of it? And you can see that this is just going to be a lot more intense thunderstorm or intensity. That's going to overwhelm the system. That's going to lead to more increased flood flows. So just an example distribution, and this is typical of Colorado and of our summer thunderstorms, is we get 50% of our rainfall in less than 20 minutes for a 1 hour storm, which means the other 50% of it is coming in over 2/3 of that hour. So that's pretty high intensity to start with. That's why we often see those big effects. So this is just an example, again, from the Lake Christine fire. So pre-fire, again, the sponge was in place. Not much was running off in the channel. We see a little bit. And the other thing is our peak here is out, I don't know, at around a little over 60 minutes. But post-fire, because it's not infiltrating, it's all pretty much going to the channel as fast as possible. We see a sizable increase in peak flows. The other thing that you see is now we're hitting that peak in like a little over 30 minutes. So not only is the quantity changed, the timing, it's running off a whole lot faster. So one of the things so those are the numbers, but what do those numbers mean on the ground? And again, this is where I really like the Lake Christine fire because it shows the two different kind of ends of the spectrum, if you will. On the north end, where things are draining into Cattle Creek, you have kind of a normal stream system. Streams, this one starts, this one adds, and they all end up in Cattle Creek. That means water gets in the stream and it kind of keeps going and it goes off in a hurry. That's what we deal with most of the time. But when you get to the south end of the fire, I'm a hydrologist. I looked at this topo map and I was like, parts of this, I really can't tell you where the water's going. Because it's all over the place. And then when we flew it on a recon, I was like, no wonder I can't figure it out because it is some lumpy, bumpy country out there. And so what that means, though, is that, water has to go a long ways. Like if something falls here, it has to go a long ways to end up getting down in here. And so it's not that continuous flow path. And so things aren't getting in this stream system and then just automatically just keep going. There's places where it's slowing down. And that can really make a difference in how those post-fire flood flows are going to go. So thinking about the other thing about the hydrology modeling is that the model assumes clean water. It's assumed it's water coming out of the garden hose, which we know it's not. And so the output that the model gives us is in cubic feet per second, which most of you have probably heard of. So a cubic foot is about the size of, say, a basketball. So it's how many basketballs are going by in 1 second. Well, if you think about, that, there's a lot of ash and debris that's in train, right? Talked about how much erosion is increased. Well, that actually literally bulks the volume. So it's not only what's the volume of water, it's how much ash and sediment is in that. So that makes one basketball actually turn into 2 basketballs because when you add that ash and sediment to it. The model doesn't account for that. So that's something that we add a bulking factor to that. But I'll be honest with you, that's one that we could use some more information or research on. But anyways, so we do try and account for that. So it's not just clean water, it's now bigger, fatter, dirtier water. So this is just the results from Lake Christine fire, and I've already hit on this, but number one, we're predicting a sizable increase in flood flows, just to use this first watershed from barely any runoff to somewhere around 50 CFS. But the other thing is that pre-fire, the time to peak was a little over 65 minutes. Post-fire, it's 34 minutes. That means if there's something downstream, if there's somebody that's in the way or that needs like a warning, there's a flood coming your way, you have a whole lot less time to get that message across. And that is actually in post-fire planning, that's one of the key things that we try and emphasize or help folks to understand as much as possible. The other thing to think about is your channel form. So if you have a V-shaped channel, you put more water in it, it's just going to get deeper and faster. That's just what's going to happen. It's kind of like when I showed earlier, the stream running through the Yampa River through the city of Steamboat. But if you have a wider channel like this one here, where water can spread out on the floodplain, that more volume is just going to spread out on the floodplain. It's going to slow down. It's going to have a whole lot less erosive effect. So it's not only the volume of water, it's how much stuff is getting into it, and it's also what kind of channel is it getting into. So moving on, talked about debris flow potential increases. And so what's interesting about post-fire is there's an increased chance of what we call channel-derived debris flows, so things that happen in the channel. But there's less potential for things to happen on the hillside. And those hillside ones are, just the slumps that you kind of look and go, wow, okay, that just happened. And the reason why is that because you're not getting the infiltration to load up the soils on the hillside as much. So the formula for debris flow, I've already talked about the loss of vegetation. You've lost that sponge, you've increased the erosion potential. And so that increased erosion potential, there's more material available now to run off. And we've talked about increased flood flows. So you add all those things together, and that is when you get a debris flow. Just talk a little more about the loss of vegetation. One thing is not only is the vegetation a sponge, it also is holding a lot of the rocks and things in place. But now that's gone, so those rocks are now available to move. And then you lose that kind of microtopography. Those things will also slow things down. But one of the big ones is that loss of riparian vegetation. So it's one thing if you have erosion or sediment getting in the stream, but then the riparian vegetation, its roughness, it helps to slow things down. But now you've also lost your riparian vegetation, so there's nothing slowing things down once it hits the channel, and that all leads to increased debris flow potential. So this is just what the debris flow model is based on. Like I said, the USGS runs this model for us, and they've calibrated it. Some things they look at: what's the historical debris flow occurrence in a certain area? Is this place just one that sees debris flows or not? And that is based on the geology and soils. Some geologies are more prone to it than others. And then the soil burn severity. Again, the more that you've lost your ground cover, that higher the potential. Your rainfall intensity, again, the higher the rainfall, the less likely you get infiltration, the more that shows up on this channel. And then, your terrain. So this is from actually Eagle Creek Fire in Oregon, but you can see this map really helps to highlight these are our concern areas. These areas, yeah, they have increased potential. I don't want to say they don't, but it's not as significant as some of these others. So again, thinking about flow paths, and I know I've touched on this, but if you put a debris flow in this channel here, it's just got a straight path that just keep on going. And so that makes a big difference. Whereas if you look at the Lake Christine, if a debris flow comes down here, it's going to settle out in this flat area before it continues on down to the valley bottom down here. So again, not to say they're not going to happen, it's just if you have those areas, anytime it drops below 6%, the debris flows just start to slow down and they just kind of, they fade away. So anytime you have these little flat areas in here where debris flow can settle out, that is a good mitigating factor. Weeds, I just want to touch on weeds. So again, after a fire, there's big potential for weeds to come in. And one of the things about weeds is that they tend to not be as good of a ground cover. And so again, you're losing your sponge potential with the weeds. So aside from all the ecological, I know changing ecology, changing habitat, changing all of that, changing forage, but they also just from a pure physical standpoint are often not as good of a ground cover. So I've talked a lot about how fires, kind of lead to the shed situation, a lot of things running off, a lot more erosion, but really, within about 3 to 5 years, you usually return to that catchment situation. And the reason for that is you get the revegetation. So that you get the fine roots start holding the soil together. They start creating organic matter, which adds to that building soil structure back together. They create the infiltration and act as a sponge. So this is just an example from a fire up in my neck of the woods where 2 years afterwards you can see where vegetation is starting to come back, and that will start to stabilize things. This is just another example of the Himman fire from 2002, and then 10 years later, it's kind of returned back to that catchment situation. So fires are just, they do have short-term effects, but usually you will return and the watershed will heal, and it will be back and kind of back to function and back to working as a catchment again. So with that, any questions?
So we'll pass a mic. Any questions? Any thoughts? Who's on the front row? Perfect.
So with the Lake Christine fire in the south end is closer to the Willits area. And you were saying that it doesn't look like that's going to slide because there's levels above it that will be more of a catchment. Is that what I understand?
More what I was saying, the potential is still there. It's just the potential for it to kind of build a head of steam and kind of come down and, let me put it this way. The potential's there, but it could be much worse. And the thing that helps to minimize it or make it not as bad is that it comes down that steep, but then it hits those flat areas, and then it, slows down, it loses steam there. And then it maybe goes over another steep area and picks up again. So I'm not saying that it's not there, but I'm saying it's a whole lot. That is a nice mitigating factor. It helps to minimize or reduce the potential. It doesn't take it away, though, completely. And just, sorry, because one of the things is how big of an effect, how big is the risk to whether it's Elgibel or the towns below or whatnot, and just really, do we need an early alert system that people need to get out, or, there are going to be some nuisances and some problems? That's what we're trying to help just provide information on. Part of the problem is that these are natural systems, and we're modeling one storm, and you don't really know what kind of storms are going to come in. So I hear that there was a 2 inches in 2 hours storm last summer, I think it was, and that led to some problems. But I'd also say that whether that's specifically the fire or that's just going to overwhelm any watershed, any location. And I think that maybe there's some problems also in Glenwood Canyon with that same storm in an unburned area that were similar. So, it's how much did the fire increase it, but there's always that potential depending on what the storm is or what happens.
So if your models have determined the places that are more dangerous, I'll call it more dangerous, like that north end. So what do you do? Does that call for different action on the part of the Forest Service or anyone else?
So it definitely does. So what you do, it depends on what you care about. And that's part of why back in my first year, I'm like, what do we care about? If it's in the wilderness and there's not a trail that's going to have a lot of people or a bridge that's, important or that we don't want to shout, it might be like, yeah, we know we're going to see problems, and we might not do anything about it. So part of it is, what do we care about? Do we care about the road? Do we care about people's lives? Do we care about somebody sleeping in a home that's likely to get taken out? So that's the first question. What do we do about it? So then, depending on what we care about, then what we do sometimes, there are things that we can do, especially when we're talking about roads and culverts. We can either pull a culvert and just put in a low water crossing. We can put in a bigger culvert so that it can accommodate more of the flood flows, those kind of things. We can increase the drainage on a road so that water, even if flood or sediment gets on it, it gets across. There's lots of things we can do. Sometimes, though, if you're talking about there is a life safety risk at the bottom of a debris flow runout, the best thing we can do is let people know. Work with the National Weather Service on an early warning system, but that is not something we're going to be able to stop. So part of it is just the education, the awareness of what the concern is, and then what is realistic to do. So the Forest Service, we provide the modeling. And again, this is just to give an idea. This isn't the end-all model because we're doing this in a hurry. And we're doing it in a hurry because we don't have 6 months to figure out if the monsoon rain is going to take something out. But also because we're just getting an idea of where those biggest concerns. But we're not going to necessarily tell the county or the private landowners what to do. But we are going to share the information, and we're going to try and help them understand as much as possible, and where we can work with them. But so I don't know if that answers your question. Okay.
Cattle Creek area, is that remote enough back there that it's not that dangerous?
I think it's. I'm trying to remember the roads. That becomes again. Is there a road or something in particular, or a structure that we're worried about? The other thing, if I remember right, there's cutthroat trout in Cattle Creek. So is there? Oh, maybe not. Okay. I thought that there were. But anyways, is there something we can do? Although I'll get specifically into fisheries. My understanding is that actually that pulse or sluggish sediment is actually not a big deal for the fish. It's the chronic slow sediment input that's a problem for them.
I have a question. Can you talk more about the geology of what you learned in the assessment of Basalt Mountain? Because it's different than everywhere else around here, it seems, or it's unique.
It is unique.
And how it plays into this.
Yeah. So I think, part of, number one is it's some limestone. So limestone it's a swirly character. Water comes and goes through limestone. It kind of creates tunnels, if you will, up in places that are karst topography. Rivers literally disappear and then reappear because they go underground, subsurface, and they come back. And so that also that makes our modeling very difficult because our model isn't used to going, wait a minute, there's places water disappears and it reappears and we don't know where it reappears. And then I think also the topography, that also then kind of leads to a not normal topography, if you will. So that normal topography would be a drop of water starts. It starts eroding a little. Some partners join it and they erode a little more, create a rill, and that creates a stream, and then it's off and running. And so Basalt Mountain really was different because the geology was not as conducive to that.
Did you just say that it's limestone and not basalt?
Well, I think there is some limestone.
Just to clarify.
No, I know. No, you're right. No, I think there is some limestone down lower on the lower pieces of it there. Sorry. Yeah, no, when you get up top, so that was the other thing is the front side, when you get up top, though, you did have that kind of basalt cap. But I think down lower that there was some limestone, if I remember right, on the lower piece of that.
Okay, we'll do another question or two. Kate.
Not specific to this area, but are you familiar with the fire that occurred outside of Durango?
The 416 fire?
Yes.
Yes.
And that caused a massive fish kill in the Animas River. Mm-hmm. And in fact, I think they're still trying to figure out whether that was just asphyxiation, oxygen, the sediment came in, killed all the fish. But there is also a theory that because of the intense temperature of the fire, it actually changed the chemistry of the soil into something that was more toxic for the fish. Do you know anything about that?
I'm not familiar with that specifically. I will say, though, that I have, I shouldn't have said that there's not a major effect on fish, but that episodic event is something that they have kind of evolved with. I have seen floating fish from fires, and so yes, I do think that the heat can affect them. I don't know enough, though, to talk on the chemical effects, those chemical changes.
All right, well, one more question.
So recently we've had some flood warnings in the basalt area. Does that have anything to do with the Lake Christine fire at this early stage in the winter, not even in the spring?
They were ice dam related, which is a whole nother really cool phenomenon. The Roaring Fork Conservancy is going to host a talk all about it, that's bringing a researcher from Wyoming, and you should check it out. Do you know about ice dams? It's pretty amazing when they break. Awesome. Yeah. Well, thanks so much for you all for coming, and we'll see you next week. And yeah, thanks again to Liz for coming down from Steamboat Springs.